In the first part of this video lecture, we discussed the context in which we are very much looking forward to replacing the Riemann integral by something which we call Riemann integral, which is much more robust and much more streamlined. And we discussed this picture that gave us an interpretation of some aspects of the context when we are defining the Riemann integral that we are not making use of, and trading that for something that we may not have in a more general context. We are now ready to move on to the axiomatic definition of the Lebesgue integral. This is not the most standard presentation in most textbooks. Most textbooks will construct it little by little with little motivation, and what we are doing here, we are defining the integral from its properties, and these are properties that we are hopefully familiar with. So we start with non-negative extended Borel function. So we in the first week we have discussed that measure theory and integration theory, it has two cases where it works very well. And the case where it works best is when a function is non-negative, because a function being non-negative, it doesn't depend on any considerations involving measures. It's just about does the function ever take negative values or not. There is a little typo here. So we consider non-negative extended Borel functions, and this is a property we are familiar with. If we integrate two functions, if we can integrate one function and we can integrate another function, then when we combine them, how can we combine functions where we can multiply them by constants, and we can also add functions. When we combine these functions in this linear way, then this linearity is respected by the integral. This is such a natural property that we have been using it since high school, maybe without paying so much attention to it. We just use it. We have to compute an integral, and we enable ourselves to just split the integral whenever we see a sum. We split the integral. And whenever we see a constant, we allow ourselves to take it out of the integral, and it will come up here. Another very natural property that we are very much used to is this one here, even though it is stated in a quite strange way. But what it is saying is when we integrate a function that has value 1 on a certain interval and has value 0 outside that interval, and this is an interval that I'm calling a, and the function takes value 1 here at a, then the integral of this function that is constant equal to 0, then it is 1, then it is 0 again, is actually the measure of this interval. And this is what this property here is saying. Another fundamental property of integrals that we have used very much in different contexts is that when a function is larger than the other, it takes higher values than the other function, then, well, of course, when you integrate that function, the integral will be larger. And finally, this is a very important property of the Lebesgue integral that the Riemann integral does not have, which is the Lebesgue integral is sigma additive, meaning if we sum countably many non-negative functions and integrate, then what the result is the sum of what we would have obtained if we had integrated each of those functions individually. And we have not yet described what this integral is. We're just assuming it exists. We're just assuming there exists this object that, given a function g, a non-negative measurable function g defined on a measure space that takes real values, so we call that extended Borel function. If we have that function, we can define the integral of that function. We can define the integral of any extended Borel function, and it has these 4 properties, this definition. These properties are, at this point, for non-negative constants, the one that we allow ourselves here, they have to be non-negative. Measurable set, so we know how to integrate functions that take value 1 on any measurable set, and 0 outside that measurable set. And we know exactly what that integral will be. It will be the measure of the set. And all the functions in these last 4 properties here, they are at this point assumed to be non-negative. And here's an exercise to practice our ability to manipulate with this abstract concept of integrating a function. And here we are being asked to show that if the set of points where the function takes positive values is 0, then the integral of the function is 0. And this is an if and only if claim, and that is for a non-negative extended Borel function. I'll let you complete all the details of this exercise. I will just give you some hints at this point. For this implication, you can compare f with a function that takes only 2 values, only 0 and plus infinity. You can compare it and use here the monotonicity property. Now, for the direct implication, we would rather do the converse of it, which is assume that the integral, assume that the set where the function takes positive values has positive measure, and use this fact plus properties of measures, in particular continuity from below, to show that, well, we can again compare, so we're again using monotonicity, we can compare this function f, so this is omega, this is the real line, and f of omega. We can find a small rectangle here whose measure on the space omega is positive and whose height is also positive. Let us call this epsilon, and then coming back here, make use of both this property and this property, the property that this epsilon can come outside of the integral. I think this is a very good exercise to start getting our hands on the axiomatic definition of Lebesgue integral for non-negative functions and understand how to manipulate measures, functions, make comparisons, and write a formal proof about its properties. It's not a difficult exercise, but it will require a lot of understanding of what has been presented so far.